This is part one of vector dot product. Okay, and I've already got the notes filled out here, and I just wanted to kind of go through and let you see what we're looking at here. So we've got the dot product, right? It's a new operation, and essentially its formula is vector A dot, and you actually say the word dot. You don't say you don't say multiply or times or anything. So vector A dot B, and in order to calculate it, determine like what the actual numerical value of the dot product is, in the end, you would just need to know the magnitude of A, the magnitude of B, multiply those, and then multiply by the cosine of theta. Now, what's theta? Theta happens to be the angle between these two vectors, A and B, okay? And so, basically, if I were to happen to have some vector A that was, this way, 2 at 60 degrees, and then I've got some vector B, which is maybe this way, 2 at 30 degrees, then the dot product of A dot B would be 2 times 2, because the magnitude of A, magnitude of B, times the cosine of 60 minus 30, right? And you just kind of take the difference between the two vectors there. And there you have it. And that's the dot product. Now notice I've given us geometric type vectors, okay? If your vectors are issued to you in Cartesian format, the dot product is done slightly differently. You remember, if our vectors are in Cartesian format, which is this new format, so it's like 2, 1 would be a vector in Cartesian, and B might be, let's say something like 1, 0, okay? And now A dot B, you're going to use 2 times 1 plus 1 times 0, 1 times 0. And that formula is written here. So it's the first components multiplied, right? The first components multiplied, added to the second components multiplied, okay? And you end up with that, all right? Yeah, there should be a 2 here, okay? Now, some properties of the dot product are listed here. So perpendicular, commutative. All right, so we'll start with perpendicular. Perpendicular dot product is basically what this means is if you take two vectors, A dot B, and this could be either in geometric format or Cartesian format, right? So, remember, this is Cartesian, this is geometric. Remember, when I say these words, Cartesian and geometric, I'm just stating the method in which the vector has been represented, or the notation with which you're representing this vector, okay? And you can convert back between the two, and we did that in the previous section, okay? Now, back to perpendicularity. So one of the properties of the dot product that it has is if you take two vectors and you dot them and the result is 0, then basically you can conclude that the two vectors, A and B, are perpendicular. And the reason that is because the cosine of 90 degrees is 0. So in this formula that I'm pointing at right here with the mouse, is, notice I would put, if A and B were perpendicular, then a 90 would go here, okay? And what's the cosine of 90? What's 0? So therefore, regardless of what's going on, you end up with a 0, all right? Another property of the dot product, is that they're commutative, okay? Meaning that, or the operation is commutative, meaning that A dot B yields the same as B dot A. So you can flip it around and it's no big deal. Other things that are commutative are multiplication and addition, right? Division is not, remember, because like 1 divided by 4 is not the same as 4 divided by 1. And so there are certain operations that are commutative and others that are not. And the dot product happens to be commutative. Associative. Associative means that you can do things in various orders and still arrive at the same answer. So I could do something like k times, k is a scalar, times a dot b, and it's equal to k a dot b, right? Well, actually, I should have parentheses here. Let me put parentheses right in here. It's gonna, there we go, like that. Okay. And or I could do k I could multiply k into b first, and then I could dot the result into a. Basically, it doesn't matter. Okay, excuse me. Or I could even dot a and b and take the result and multiply it into k, right? It doesn't matter. It means it's associative property. And all of these, if I do it in all three of these different ways, I'm going to end up with the same number. Okay, distributive property. The dot product distributes over addition, meaning that a dot b plus c is the same as a dot b plus a dot c. Okay, and so you end up with that. Okay. Okay. Now, here we go. So next thing, what I want to do is I want to mention here, we're going to imagine what the dot product is geometrically. We're going to use geometry to interpret the dot product. All right. So I'll start with the formula. All right. And I'm going to erase this so that I can redo it. There's like a flashlight there. All right. So basically, I've got like this little circle going on here. So A dot B is really just A magnitude times B magnitude cosine theta. If you break it into these sort of things here, I'm going to go ahead and break it into here. So I'm going to separate A magnitude, and then I'm going to write here B cosine theta as its own concept. So that's what this orange underline is. Okay. So I'm going to start out with two vectors, B and A. All right. And so there it is. So what I'm going to do is I'm going to take these two vectors and I'm going to put them like this. All right. My goal here, remember, is to imagine conceptually and geometrically what is the dot product. What is it? So basically, if I take this B here and I take this A, if I want to imagine what would A dot B look like geometrically, then what I would do is I would first imagine B and A in this format. Okay. And now what I would do is I would take B cosine theta. Okay. Theta being the angle between A and B. So that's this. B cosine theta is the adjacent side to that angle. Okay. Just using a little bit of trigonometry, you can see that this is B cosine theta. And now this B cosine theta is now this green, sort of greenish vector, right? And A magnitude is this longer vector here. And now the dot product is simply A magnitude times B cosine theta. So now if I take A magnitude and I draw it here, and I take B cosine theta and I put it right there, and I conceptualize or just imagine a rectangle, the interior area of this rectangle here, whoops, I erased my thing there, is the interior rectangle there is going to be A dot B. All right, it's going to be A dot B. Okay, and basically, if that's just a geometric interpretation of what is the dot product. What is it? All right. Now, the dot product has various now applications to it, right? And so, because of this, the results of this geometric interpretation, you can actually use this concept in physics and actually economics. There's you can use this in a wide range of applied math and sciences. Okay, and so we'll do those in the next few examples here. All right. So we're going to go ahead and calculate the dot product of vectors. Two vectors that are represented. That are presented in Cartesian form. I actually did this incorrectly. I started with some Cartesian vectors. So change this geometric to Cartesian. So let's calculate the dot product of two vectors that are presented in Cartesian form. Okay. So basically, I'll start out with two vectors, 2, 4, and 3, -1. Okay. And now, if I just take a look at what this is, A dot B, it's basically 2 times 3, or these two components, right, plus the product of those two components, and I end up with a 2 as the answer. But what is that? Like, what does it represent? All right. I'm going to go ahead and draw that out, perhaps over here, adjacent. Well, maybe I can do it right down here. Maybe I'll have enough space. So I'm going to start with 2, 4, and 3, -1. Okay. So 1, 2, 1, 2, 3, 4. That's vector A. Right. Oh, and you know what I'm going to do? I'm going to turn on grid lines here. And this is going to help out a lot. So I'm going to erase this. All right. So I'm going to go ahead and do 2, 4 now. All right. So here's 2. Here's 4. This is vector A. And then 3, -1 is vector B. All right. Okay. And now, basically, what we're wanting to do here is 3, -1. I should have done something different, maybe like 3, 0 or something, because this basically what I want to do now is I'm wanting to drop this vector down. Remember, theta is in here. Okay, theta is in here. And now b cosine theta would be essentially, if I were to sort of somehow drop down a right angle like that, and now I've formed this very small triangle here. All right, it's very small. And I'm going to go ahead and imagine this little section right there. That's b cosine theta. All right. And then A is this. All right. And the result of A dot B, we know is 2. So basically, if I take A, which is maybe something like this, let's say A is about that long. This is A magnitude. Okay. And then I take B cosine theta, and I put it right there, right? And I make a box Okay. What's the area of this box? Turns out the area of this box is 2, because this is about a half. That's another half there, so that's 1, almost 1. There's another half and another half, and then the little bit left over there is going to be the area of 2, and that happens to be A dot B. Okay? So I wasn't saying, I'm not saying that that's no application question right there. That's just simply the sort of essence of the dot product, a geometric interpretation of, the act of taking 2 times, the act of taking 2 times 3 plus 4 times -1 and getting the answer of 2, right? How would a mathematician imagine this? So the way that you would imagine this is you would say, look, all right, you basically take B and you would say this is what's called projected onto A, okay? Or take B cosine theta. And then that little arrow you put right there. And then you take A itself and put that there, build a little rectangle, and the area of that rectangle is the conceptual result of it's the same idea as taking the dot product of A and B, okay? All right. Taking the dot product of vectors that are in geometric form, okay, is no big deal. So I'm going to go ahead. Let's say I've got 2 vectors, vector here, which is A, which is 3 at 12 degrees, and vector B is 7 at 85 degrees, okay? And so A dot B would be 3 times 7 times the cosine of 85 minus 12, or the difference between the angles, remember. Because remember, this theta is the angle that's formed by A and B. So if B is at 85 and A is at 12, then the difference between them would be whatever, 70 something or other, 73, okay? So you put a 73 degrees in there, you calculate all that out, you end up with 6.1, right? And you think to yourself, okay, well, that's all great, but what actually happened there, all right? Anyway, so what I'm going to do is I'm going to say, all right, well, this is what happened. Look at what happened now. Here's B, right? And here's A. I'm going to take B and I'm going to imagine projecting it onto A. And there it is. It's that green/black vector there. I'll take that green/black vector and put it here. All right. Then I'll take A itself and I'll put it here. Okay. Notice this green/black vector is about 2 units long. And A is exactly 3 units long. Look, the magnitude of A is 3. You see that? So what's 2 times 3? It's around 6, okay? So that is, again, what is the geometric interpretation of B. It just so happens in this question, the vectors were given to us in geometric notation. In the above question, the vectors were given to us in Cartesian notation. But conceptually, the idea, the concept is exactly the same concept, all right? And so let's go ahead and take a look. And that was it. And some applications of dot products that's coming in a separate video, all right? That was sort of the idea of the dot